The notion we want to understand next is the notion of differentiability. And let me just remind you what we've seen already. So if we have a function of two variables, a scalar function of two variables, there's the notion of partial derivatives at every point, if they exist. And those partial derivatives somehow only cut slices parallel to the x and y axes and regard the function as a single variable function and form these two lines, these two tangent lines at the point only in the x direction and the y direction. These two lines give rise to a plane, and that plane is our candidate for the tangent plane at the point. Everybody remember that? Okay. Now the issue is that the notion of partial derivatives is not sufficient. In what sense? In the sense that the partial derivatives can exist without the function actually being smooth, without what we see being some smooth surface. And we saw an example, this rooftop drawing that we made, where in the x and the y direction it looks very smooth, but in any other direction it's very cuspy. Okay, remember that? So we need a stronger notion, a more powerful notion that would actually be equivalent to having a tangent plane. Okay? In single variable calculus, the notion of being differentiable, which was having the derivative, was precisely equivalent to having a tangent line. That's how the tangent line was defined. Remember? Okay? But here, something is more subtle, something more complicated is going on. So this is the notion that we want to develop, and we'll see that this notion fits in the broader picture more nicely than just the notion of partial derivatives. In what sense? For example, a differentiable function will always be continuous. So just like in Calc 1, differentiability is going to apply continuity at the point. And so what we want to do is find what is this mysterious notion. It's not that mysterious, but I made it mysterious. So let's figure out what it was. And in order to do so, I want to take a step back to Calc 1 and discuss the notion of differentiability in Calculus 1 in single variable functions, but from a slightly different point of view. So back to functions from R to R, to single variable functions. And it's a theorem. I want to write it as a theorem. So the theorem is the following. F of x, single variable function, is differentiable. This word is way too long for me to write it again. So diff is going to be differentiable. At the point x0, if and only if, so first of all, what does it mean to be differentiable at a point x0? Okay, this just means, let me remind you, a function is differentiable if the limit as h goes to 0 of f of x0 plus h minus f of x0 divided by h, if this limit exists. That's what it means to be differentiable. And then we call this limit f prime at x0. So being differentiable is just the existence of this limit. Everybody knows that, right? Hello? Okay, thank you. So I want to say something which is equivalent to this. It's going to look strange at first, but the proof of this theorem, which we're going to see, is a two-line proof that says that it's precisely the same thing, just a different way of looking at it. So if there exists a certain number, which we're going to call a, so this is just a number, a real number, a and r, such that f at x0 plus h minus f at x0 equals a times h plus alpha of h times h, a times h plus alpha of h times h, where alpha of h approaches 0 as h tends to 0. Okay? So it looks somewhat weird, okay? But I want to show you that this statement and the existence of this limit are precisely the same thing, are just different ways of saying the same thing. So it's an if and only if theorem, so I have to prove two things. I have to prove that if this limit exists, then I can write this thing. Note that this thing is an equation. This is not a limit statement. It's an equality at every point where one of the ingredients is a function that tends to 0. Okay, so that's the difference. Okay, so let's prove it. So there are going to be two directions, and let's start from the direction from this direction. So I want to show that if this happens, then the function is differentiable. So let's do that. So proof. So first I'm proving this direction. Suppose f satisfies, and let's call this entire thing, look here a second again, let's call this entire thing star. Okay, so I don't have to write it again and again. So this is star, and differentiability is that. So back here, suppose f satisfies star, and we want to show that that limit that defines the derivative exists. Then, what is f at x0 plus h minus f at x0 divided by h? What is this thing? Well, by star, this statement was that I can replace f at x0 plus h minus f at x0 by ah plus some function alpha of h times h, all of this divided by h. That was star, right? This in turn equals a plus alpha of h. Do you agree? And when h goes to 0, star assumes that alpha of h goes to 0, right? That's given when we're proving that direction. So this goes to a. Do you agree? So what did we just show? We showed that if star holds, then the limit of this thing as h goes to 0 exists. That's precisely saying that the derivative exists, and we even know what it is. So there exists f prime at x0, which is the limit of this as h goes to 0, and we even know what it is. It's that a. That a is none other than the derivative at x0. Is that clear? Okay, did everybody follow? Okay. Now let's do the other direction. Now I want to prove, I'm going to assume that the limit exists, that the limit of this thing as h goes to 0 exists, and I want to prove that this star criteria holds. So this is the proof of the other direction, this direction. Assume f prime at x0 exists, and we want to prove star. Okay? Now, the proof of the previous direction gave us a clue. Okay? In order to prove that this property star holds, I have to build two ingredients. I have to find this scalar a, capital A, that does something, and I have to find this alpha of h function that goes to 0, right? Those are the ingredients in star. But the proof of the other direction told me what the a I'm looking for is, right? A is going to be the derivative. So define a equals f prime at x0. F prime at x0 exists. That's the assumption of this direction. Okay? I'm going to call it a. And now what do we have then? F at x0 plus h minus f at x0 divided by h. The limit of this thing as h goes to 0 is a. right? Because the limit of this thing is precisely f prime by definition, and we called f prime a. Do you agree? Okay. Therefore, by limit arithmetics, a is just a number. The difference of f at x0 plus h minus f at x0 divided by h minus a, this thing goes to what? Right? So this is just naive limit arithmetics, right? And let's call this entire expression, let's call it alpha of h. So the only thing confusing about this proof is remembering the directions. Remember what is the data and what you need to prove. In this direction, we know that f prime exists. We need to prove that star property, that we have this equality where we have some alpha of h that goes to 0. So I can prescribe what a is, what alpha of h is, as long as it satisfies the property star. Clear? So I'm calling f prime of x0, I'm calling it a, and now I'm calling this entire difference, I'm calling it alpha of h. It's clearly a function of h, right? x0 is fixed and a is fixed. And then, what happens here? If this is alpha of h, then alpha of h times h is what? Alpha of h is this entire thing, times h, it's this times h, so it's f of x0 plus h minus f of x0 minus a times h. Do you agree? Good? And therefore, if you move this to the other side, you get precisely that f at x0 plus h minus f at x0 equals a times h plus alpha of h times h, where alpha of h satisfied that it goes to 0 as h goes to 0. And this was precisely, this entire statement here, this is what we call star. This is what we need to prove. Okay? So, if you think about, if you just got confused, then look at it again later, and you'll realize pretty quickly that there's really not, we didn't say much. We just wrote the same thing in two equivalent ways. Okay? And the reason for doing so is that that equivalent way is going to be easier for us to generalize to the two-dimensional definition of differentiability. Okay? Okay, so back to the original theorem. So the theorem said, differentiability for single variable functions, which was originally defined as the existence of the derivative, namely the existence of this limit, can equivalently be written as this property, which is comprised of two lines, so it may look more complicated, but it's just the same. It's saying exactly the same thing. That the difference between the value of the function at the point and the value of the function near the point, okay, is some number times the distance between the two, h, plus some function of h times h, where that function goes to 0. Clear? I want to generalize this. And the generalization of this is going to be how I'm going to define differentiability for functions of two variables. Here goes. So now we're returning to our Calc 2 functions of two variables. And here's the definition. This definition is a mouthful. It's going to scare you when you first see it. But when you think about it just for a couple of seconds, you'll see that it's just the generalization of that. Okay? So let f of xy be defined in some neighborhood of x0, y0. So this is the point we're looking at, and we're assuming that the function is defined in some neighborhood of that point. We say that f is differentiable at that point if, and now I want to write that star property. So there was an A there, and there was an alpha of h, right? So now there are going to be an A and a B, and alpha is not going to be just of h, it's going to be a function of two variables. Okay? So if there exist two numbers, A and B, these are just real numbers, such that when we take points near x0, y0, and we look at the difference, so f at x0 plus a small increment, which we're going to call h, and we want to allow a small increment in y, but not necessarily the same. We want to have all points around it, so the y increment we're going to call k, okay, to distinguish the two, minus f at x0, y0. That's the difference between the value near x0, y0 and the value at x0, y0, right? Equals this a times h. H is the difference in the x-coordinate between the 2 points, plus this b times k. K is the difference in the y-coordinate, right? Plus a function of the two variables, alpha of h and k, times, now we want, so in the star property, in the single variable version, it was this function times h, where h was the distance between the x components, there were only x components, near the point and at the point, right? Now I want here the same thing. I want the distance between this point, and that distance is precisely the root of h squared plus k squared. Okay? Do you see that this is a two-variable version of the property star? Do you see the resemblance? Okay? And now that property has a where alpha of h goes to 0, same thing here. Where alpha of h and k goes to 0, as hk both tend to 0. So this is two-variable convergence. Okay? So how many, raise your hand if you're terrified at this moment. Okay, good. We can, just you. No, I'm just kidding. Okay, so do you see that? Do you see even in the technical level? Do you see that this generalizes that property? Okay, did you see that property, that I mean star? Did you see that is equivalent to single variable, to being differentiable in the single variable sense? Okay, so it makes sense to call this differentiability in the two variable sense. Okay, and what we don't have here is a limit. Okay, the limit is somehow a limit of this component here. It's not defined being via, like differentiability for one variable was defined via the derivative. F prime at x0. There's no analog here. There's no number that we call the derivative at the point. Okay? There are these numbers, and those are the partial derivatives. Okay? But the notion of being differentiable is somehow more complicated. But it probably is related to those partial derivatives, right? Okay? And it is. Just like in the single variable case, that a was the derivative, here, this is going to be the partial derivative with respect to x, and this is going to be the partial derivative with respect to y. Okay? So they are going to be related. We'll see that in a minute. Okay. So before we prove some theorems and do some examples, I want to give some equivalent definitions of the same thing. So we'll have them all along, okay? So that they're equivalent in oh, I have a blue already. They're equivalent, and we're going to use these equivalent definitions throughout, and there are many of them. It's just different ways of writing. Just like for single variable, we had, instead of writing the limit as h goes to 0, sometimes we wrote the limit as x goes to x0. Remember that? Okay, so we're going to have some equivalent definitions here. So let me write a few of them. So equivalent. So sometimes you'll see, let's go back to the definition we wrote here, and some of them I'm just going to write on this. So sometimes you'll see, instead of writing x0 plus h and x0, you'll see that this is called x, and this is called y. And then, what is h? Just like in single variable. If I replace x0 plus h with x, then what do I need to replace h with? Exactly. So you'll see sometimes that instead of x0 plus h, you'll see x and y. And then you'll see here, instead of h, x minus x0, and instead of k, exactly, y minus y0, and likewise throughout. Okay? So is that clear? It's the same idea. Okay? And so that's one equivalent definition. Another equivalent definition is, and that's a bit more complicated to show that they're exactly the same thing. I'm just going to write it so in case you encounter it. I'm usually going to use this one, but I'm going to write the other one in case you encounter it, that you don't freak out, that you know that it's actually just a different way of writing the same thing. So equivalent, fxy is differentiable at x0, y0 if f of x0 plus h, y0 plus k minus f at x0, y0, so far there's no difference, equals a times h plus b times k plus, and now we're going to have two functions, alpha and beta. And alpha is going to be a function of h and k only multiplied by h, and beta is going to be a function of h and k only multiplied by k, where both functions tend to 0 as h and k tend to 0, of course. Okay, so we had equivalent definitions of the limit kind of along the same lines, if you recall. Okay, one definition of the limit was with the root of h squared plus k squared, the distance in the delta component of the definition, and another was saying only the x difference is less than delta and the y difference is less than delta separately. Remember that? Okay, so this is kind of the same sort of equivalence of definitions. Another equivalent definition, is to define it via a limit. Okay, so f is differentiable at the point if, and now there's going to be a big scary limit here, the limit as x, y tends to x0, y0 of, there's going to be a big fraction here, of f of xy minus f of x0, y0 minus, now I'm going to cheat a bit. One of the theorems that we're going to see, one of the first theorems we're going to see, which I already hinted, was that those a and b are the partial derivatives. Okay? So I'm going to write that already. Minus df to dx at the point x0, y0 times x minus x0. So this is a. This is just this a. We're going to see that. And again minus df to dy at the point x0, y0 times y minus y0. And this is none other than b. And again, we're going to prove it in a second for the original definition. And divide all this by the root of x minus x0 squared plus y minus y0 squared. And the definition is that this nice, friendly-looking limit is 0. And in fact, this is easy to see. Easy is after I show you it's easy, but it's really easy. Okay, why? Because what is the numerator of this entire expression? So it's, remember that x is, you can replace x with x0 plus h and y with y0 plus k, and then this is h and this is k, right? That we already discussed. So what's written here is the difference between f near the point and f at the point minus the two things that were written on the other side in the original definition. Okay, so I want you to recognize the numerator. Let's go back one board. The numerator is everything you see here except this. Do you see that? With moving these to the other side. So it's f at xy minus f at x0, y0 minus a times x minus x0, because a is the partial with respect to x, minus b times y minus y0, because that's k, and b is the partial with respect to y. Do you see that this entire expression, that's the numerator of that fraction over there? Do you see that? Okay. And if I move these to the other side, then this equals, with these at the other side, it equals this, right? Do you agree? So I can replace the numerator by just this thing. But then I'm dividing by this. I'm dividing by the root of x minus x0 squared plus y minus y0 squared. So the entire thing in that limit is just alpha of hk, or alpha of x minus x0, y minus y0. Do you see that? Okay? So the statement is that that limit, the difference between this minus this divided by this, goes to 0 as hk goes to 0. Do you see that? Do you see the equivalence of these two things? Okay? So I'm usually going to use this, and usually, in order to calm you a bit, we're not going to use it a lot. We're going to use it to prove some very key properties of differentiability. And then we're gonna put that notion of differentiability aside, because there's going to be something slightly stronger and much easier, much more tangible, much easier to handle, that's going to replace differentiability for us. But that's going to come a bit later. Okay, so 3 equivalent definitions of being differentiable, all of which are 3 lines long. Okay, and all of which clearly, if you want to take a function and check if it's differentiable at the point, there's going to be work involved. Do you see that? It's not going to be like something for free. Okay? So what I want to do next is, first of all, maybe do an example, check if a function is differentiable at a point, and then prove some key theorems, build the broader picture. For example, show that these a and b are not just numbers, they're actually the partials. And show that if a function is differentiable, it's automatically continuous. Okay? And discuss the correspondence between being differentiable and having a tangent plane. And they're equivalent also. A function is differentiable if and only if it has a tangent plane. Okay? So all that is coming up next.